Fine-tuning? No, this is not agentic. AI, no, this is not automating something. We are trying to showcase how internal structure of LMs work and how we can make a model better at something without building a whole GPU factory. I'm training a large language model to play Snake, Mario, and soon even complex 3D games. Not by writing explicit rules, but by showing the AI the game screen and letting it learn. The technique behind this is called fine-tuning, but to really understand how it works and why it's so powerful, we need to look under the hood at the billions of numbers that make a neural network tick. Today, I'll explain exactly how fine-tuning changes those numbers, how we shrink models from terabytes to megabytes using quantization, and how a tool like Unsloth makes it possible on a single free GPU. No fluff, just the mechanics. A modern language model like Qwen 2.5 is, at its core, a giant mathematical function. It's made of stacked transformer layers, each containing attention mechanisms and feed-forward networks. The knowledge of the model is stored in its parameters, the weights and biases of all these connections. When I say Qwen 2.5 has 1.5 billion parameters, I mean there are 1.5 billion individual floating point numbers inside it. These numbers were determined during pre-training on vast text corpora, and they encode general patterns of language, reasoning, and even some world knowledge. Every time you give the model a prompt, it performs a cascade of matrix multiplications using these frozen numbers and produces a probability distribution over the next possible word. Change just one weight slightly, and the entire output can shift. The art of fine-tuning is to carefully nudge the right weights, so the model becomes an expert at a particular task, like playing Snake without ruining everything else it already knows. If we tried to update all 1.5 billion parameters directly, we'd need to store not only the model itself, but also the gradients and optimizer states for each parameter. That can easily require over 30 gigabytes of GPU memory, far beyond a consumer card. But there is a clever insight. When adapting a pre-trained model to a specific task, the necessary changes to the weight matrices are often low rank. That is, the update DW can be expressed as the product of two much smaller matrices, A and B, where A and B have far fewer parameters. This is exactly what LoRA low-rank adaptation does. Instead of modifying the original weight W, we keep it frozen and add trainable matrices A and B alongside it. The effective weight becomes W plus A times B, scaled by a factor. During fine-tuning, we only optimize A and B. The original billions of parameters stay untouched. This dramatically reduces the number of trainable parameters, often by a factor of 100 or more, and makes fine-tuning memory efficient and fast. So what happens when we fine-tune on a game like Snake? We create a data set of thousands of examples. Each example pairs an input, a text description of the game board, or later the raw pixels, with the correct output, a single action token like up. During training, the input goes through the frozen base model and the LoRA adapters, producing a probability distribution over all possible tokens. The loss function, cross entropy, measures how low the probability of the correct action is. And if we add reinforcement learning, where model learns by its own mistake and improving it as per the PPO, then it starts to make itself better at particular task. And as soon as the model understands the pattern boom, we have a beast in a domain which consumes very less hardware,